So I mentioned in one of the previous videos that when you've got a problem that's exponential growth or exponential decay, that it's automatically in the the P equals CE to the KT family, and that's true. But as soon as we put it in the CE to the KT family, this automatically means that we're going to need a calculator. And the reality is we actually don't always need a calculator for these. Sometimes they can be done without, and there's sort of a different way that you can look at them. And that's sort of what I want to show you through these two examples that I have in this video. So let's take a look at the first one. So an initial population of 32 butterflies grows to 48 butterflies in a 5-month period. And you know what, I just realized I'm missing a word here. Really what this problem needs to say is it needs to say that it grows exponentially. Right? Because if you think about it, there's really sort of two different ways this growth could be happening. It could be happening in a linear fashion. And what does a linear fashion mean? Well, it means that, that at time 0, there were 32 butterflies. And at time 5, there were 48 butterflies. So what happened from here to here? Well, it grew by 16 butterflies. So if it was linear, in the next 5 months, it would go up 16 more butterflies, so 64. In the next 5 months, it would go up by 16 butterflies again, so that would be 80. And this is called linear because it's making this line of values. You're going up 16 to here, to here, to here, to here. If you plotted these values, you would get a straight line graph. Right? But that's generally not the way things work with growth. It does sometimes, but especially with natural growth, it just doesn't happen that way. With exponential growth, it's not about adding something each time, but about multiplying by something each time. Right? So when we have exponential growth, if you've got 32 here and 48 here, the growth rate is basically 48 over 32, like the end population over the beginning one. And if you simplify that, that ends up being 3 halves. So what that means is that we are going to multiply by that growth rate 3 halves each 5 months. Right, and I hope that makes sense. Like, it basically means that in exponential growth, when time is 0, we were at 32. Then, if I multiply by 3 halves, sorry, I'm writing really quickly and sloppy, that means that when time is 5, I'll be up at 48. Now, if I were here to multiply by 3 halves again, when I get up to time 10, let's see here, dividing 48 by 2 is 24. 24 times 3 is 72. Great. If I wanted to know at time 15, well, I would just multiply by 3 halves again. 3 halves divided by 2 is 36. 36 times 3 is 108, and so on. And so what you're seeing happen here is in the beginning there was a growth of 16, then there was a growth of 24, then there was a growth of 36. Each time you're growing by more and more and more each time. It's exponential growth. It's not linear growth. So that's the idea behind these problems. And so now what's interesting is, now that I've done this, I bet I've accidentally answered all of my questions. So let's go back and look at what my questions actually were. The question said, okay, how many butterflies will there be 10 months from now? Well, as I just explained, if you started with 32, you multiply by 3 halves to get 48. If you multiply by 3 halves again, I think if you look at your notes, I think we said that was 72. So in 10 months, there will be 72 butterflies. And in 15 months, I think we wrote that one down as well. I think that one was 108. Scroll down and take a look. Yeah, 108. And I got those by just taking that growth rate and multiplying it each time period that passed. Now, part B, give an approximation for the amount of time it'll take for the population to reach 200. Well, we can sort of keep running this process, right? If I were to do, time 20, I would just have to do 108 times 3 halves. That'll be 54. And so understand all I'm doing here is I'm just doing 108 times 3 halves. You simplify this down to 54. 54 times 3 will give you 162. Time 25, we can do 162 times 3 halves. 2, and this will cancel down to 81. 81 times 3 is 243. Okay, and so 200 happened somewhere in between these two things. You know, did it happen at exactly 22.5? No. You know, it probably happened somewhere around time 22. You know, could we find out exactly? Sure, we could. We could set up we could set up one of the actual, P equals CE to the KT things. But if I don't have a calculator, then I can't do that. So the point I wanted to get at here is just that these problems can be done without a calculator. You just have to be able to see what that growth rate is. With that said, we can also do the decay problems without a calculator as long as they're set up properly. And it's the exact same principle, right? So let's take a look at one of those. And I had fun with this one. It was during lunch that I wrote this problem, and apparently I was hungry. The rate of change of the number of chips in a bowl at a party is directly proportional to the number of chips currently in the bowl. Now you're like, oh my god, what the heck is this? I'm just looking for exponential growth. Why are you going crazy on me, Phelps? Remember that 2 videos ago, I think I said that if you make the statement, the rate of change of the number of chips in a bowl is directly proportional to the number of chips currently in the bowl, that phrase right there really effectively means that this is exponential growth or decay. Right? When you see that phrase, this rate of change phrase about the number of chips being proportional to the current number of chips, that means exponential growth. And what does exponential growth mean? It means either CE to the KT, or it means that there's some multiplied constant growth term as we're going through it, right? So what is the growth rate? And actually, these are chips in a bowl. They're not growing. This is actually the decay rate. And that's not because they're old and getting moldy. It's because people are eating them and the number of chips in the bowl is decaying, right? So what's the decay rate? Well, it's the final 32 divided by the initial of 128. That simplifies down to 1/4. Now, what does that mean? That means every 3 minutes that go by, the number of chips in the bowl is decaying down to 1/4 of the original amount, right? So just like we did on the previous problem, I kind of feel like we might as well just start looking at this, right? When time is 0, there are 128 chips in the bowl. How do I find out what happens at time 3? Well, I'm just supposed to multiply by 1/4. At time 3, there are 32 chips in the bowl. How do I figure out what happens at time 6? I multiply by the decay rate, the growth rate of 1/4. Now I'm down to 8, right? And I could try and squeeze one more in here. What happens 3 minutes later at time 9? Again, I multiply by 1/4, and now I'm down to 2 chips in the bowl, right? And so it's actually kind of funny. Without even looking at my own questions, I think I answered them. How many chips will be in the bowl after 6 minutes? Well, after 6 minutes, there will be 8 chips in the bowl, right? How long will it take for there to only be 2 chips in the bowl? Well, we just found out that was time 9, so it will take 9 minutes, right? Mathematically, that's the end of this video, but I wanted to take a minute to convince you of the idea that I think this is actually a reasonable question. I don't think this is crazy. Like, if you think about it, when you put a giant bowl of chips on the table, like if you put 128 chips on the table, it's totally reasonable that after 3 minutes, almost all of them are gone. But the rate at which people eat chips isn't the same, right? Like when there are fewer chips in the bowl, people take fewer of them. Maybe it's because they've already had chips. Maybe it's because they don't want to take the last one. Like I see that being this, right? Like when there are 8 chips left in the bowl and there's a bunch of people sitting around, you don't want to be the last person to take the chip. You're looking at it going, man, if I take the last one, I have to get up and get more. Like, I don't want to do that. There's this sense in which the rate at which chips are taken from a bowl is probably not linear. Now, I'm not going to say that it's perfect exponential decay either, but I am going to say I think there's some value in us seeing this and seeing that this does apply to party planning. So for those of you that feel like you're never going to use calculus, if you like chips, you should like calculus. That's the end of this video. I hope you had a good time, and I'll see you in the next one.